All right, so I just want to go back to the problem that we were looking at, which was the acetic acid. And we went through and we kind of figured out what the pH of this buffer solution was going to be. And we said it was a buffer solution because we did have our weak acid. Also, we had our conjugate base here. We had a 1.0 molar of each. And we kind of went through this process of simply saying, hey, I'm going to first start off with the fact that I have 1.0 molar of the weak acid, 1.0 molar of the conjugate base. And once again, this is just like a common ion sort of problem, where we go in and we say, hey, you're minus X plus X plus X, we have 0 here, and therefore we end up with a 1 molar minus X plus X, and then a 1 molar plus X sitting right here. If we look at our Ka expression, then once again, products of reactants, everybody raised their coefficients, no solids, no liquids, so here's my Ka. What I did over here on the board is I went over here and I kind of substituted in. I said, hey, for the hydronium cation, because if you look at it, remember, we already said that when we did the test, this minus X and this plus X can be eliminated. Which means that what I have here is this X, of course, will sit right here, and I'll get 1 molar here and 1 molar right here, and the Ka is going to be sitting right here. So all I did is just kind of substituted into that equilibrium expression. Clearly the one's going to cancel out. We said, hey, in this case, that the X is going to be equal to the hydronium cation concentration, which is equal to, once again, 1.8 times 10 to the 5th. Took the log of it, or negative log, and we found the pH in this case to be 4.74. So this is one way in which we can actually solve a buffer problem as far as figuring out what is the pH of a buffer solution. But in a second, I'm going to show you a much faster way that does not require me to go through the ice table. I don't have to set up this equilibrium expression. And basically what's going to happen is I'll just take my numbers that are given to me, such as the concentration of the weak acid, conjugate base. I'll throw it into the equation we're going to look at, which is called the Henderson Hasselbalch equation. And it's going to just spit out that, hey, the pH is going to end up being 4.74. Now, before I do this, there's one thing that we need to look at here. If I have a buffer solution, so here goes my buffer solution. And I'm going to make this, instead of the acetic acid and the acetate as the weak acid conjugate base, I'm going to go back to the HF scenario in this case. And it's just easier for me to write the HF. I can write this one here as well. But HF is just a small acid, where acetic acid, I got the C2H3O2, just like a lot of space here. So here's my buffer solution sitting right here. And once again, I got my weak acid here. And here goes my conjugate base. And once again, both are ready. They're just sitting there, ready to attack in this case. One of the things that we can see here is that if we looked at the actual, just the Ka expression, so the equilibrium expression of this, it would look like the following. Ka is equal to products over reactants, let me do this really quickly, HF aqueous plus H2O liquid, and equilibrium to produce the H3O plus aqueous plus the F minus aqueous. So once again, this is like an acidic buffer solution. So that's what I got here. So if I go in here and I write, once again, the Ka, since it's an acidic buffer solution, I can say, hey, this is going to be H3O plus F minus divided by HF. And I'm just going to do what we did a second ago earlier in class, where I'm just going to solve this thing for H3O plus. And when I solve it for H3O plus, I'm going to get something that looks like this right here. So I'm just going to isolate this, so it's going to be Ka times HF, all divided by, in this case, the F minus. So one of the things that I know is if I can keep these two numbers the same, then in a sense, I can keep this hydronium cation concentration pretty much the same as well. Just like, for instance, one of the things we said is that if we had something such as a 1 molar of each one, and if we had 1 molar of this one, 1 molar of this one, then they would cancel out. And then once again, the H3O plus is just going to be equal to the Ka. Now the problem that I run into here is we saw that when it came to neutralization reactions, the neutralization reaction that caused this ratio to change. We said that, hey, if we go in here and we dump in something such as H3O plus, then I know what's going to happen here. We said, okay, that base right there is going to go on attack. And as the base goes on the attack, it's going to say, okay, let me attack, in this case, that hydronium cation. Neutralization going to completion, HF, plus I'm going to get H2O. So I can clearly see that what's going to end up happening here is this ratio is going to change a little bit. And if it changes a little bit, then it's going to affect the H3O plus, which of course is going to affect the pH here. All right. And once again, we already talked about this. We said that, hey, if we use up some of the conjugate base, then of course that means the solution is going to net become a little bit more acidic in this case. Because we know that what's going to happen is this is going to increase based upon the neutralization. This is going to go down, which means that the H3O plus is going to go up just ever so slightly, just a small amount. Now, the degree at which this thing possibly goes up is really based upon my initial concentrations of the HF and the F minus. And let me explain what I mean here. If I have a lot, and when I mean a lot of HF, and if I have a lot of the fluoride in this case, and we're going to talk about this in a second because it's going to be called the buffer capacity. If I have a lot, say I have 1 million of these here, and I also have 1 million of the fluoride sitting right here. If I were to drop in just one of the hydronium cations, then that means that I would have, in this case, 1,000,001 of these, because it would just say, hey, one of them's going to shift over here. And then here, I'm going to have 999,000, and we can clearly see it's just going down by 1 in this case. But for all practical purposes, when you do the math between those two, they're going to still be the exact same number. The problem becomes with buffer solutions where we can't have really big kind of fluctuations play out here is when we end up having something where these concentrations are pretty small initially. If they're pretty small initially, then what's going to end up happening is we're going to get a really big swing that's going to take place with this actual pH. So to give you an analogy here, let's just say that I had over here, going back to scenario, I got 3 HFs, 3 of the fluorides right here. If I was to have one of the neutralizations kind of play out here, so one of the neutralizations go through, then what's going to end up happening is one of the fluorides is going to be removed, so it's coming out. And it's going to interact with the H3O plus, so it's gone. But what I'm going to end up getting here is I'm going to get an additional HF being produced. So when I look at it, it's going to have some bearing on this actual ratio here. And if somebody added another H3O plus here, so I'm adding another one in this solution, then what's going to happen is this fluoride is going to say, I need to neutralize you. And once again, I can clearly see I get more fluoride and I get more of the weak acid, and I got less of its conjugate base. Things are going to fluctuate even more. If I have low concentrations of each one of these, you're going to get a really big fluctuation. But at the same time, if I had 1 million of these HFs here, and 1 million of the fluorides right here, then this ratio is not going to, will it change? Yes, but it will be minuscule. Very, very, very small. And because of that, one of the things that we're going to see when working with buffer solutions is we're always going to start off with a very high concentration. So I want to have a high concentration of the weak acid and its conjugate base. Even the analogy, if we go back to the analogy of where we had the gladiator and Athena, if I only had one gladiator and we only had one Athena, we'd have problems. Because if they sent two people over the border and we said, I remember, Athena, she was a conjugate base. So if they sent, once again, Athena, which we said was like the F minus, if we only had one Athena and they threw in one of the H3O plus, it's like, hey, I'll neutralize you. But there's a problem, there's no more Athenas, which means there's nothing that can kind of go in and neutralize the next H3O plus that comes through. And we'd really miss Athena. We'd be like, no, we don't have Athena here. But at the same time, if I had something like 1,000,000 Athenas on the border, 1,000,000 of these fluorides sitting right there, if one of the Athenas had to go in and neutralize and get rid of, once again, the Athena because she's turning over here, they're going to be like, okay, well, we still got a lot of them sitting there. And once again, it's not going to cause that ratio to fluctuate very much, which means that H3O plus is not going to fluctuate, and my pH is going to pretty much remain the same. Why do I point this out, and why am I going through this? One of the things that you'll notice here in the notes. I'm going to pull up. Here we go. This was that acetic acid problem that we're looking at in the class. And for this acetic acid problem, what I'm telling you here is that this ratio right here is directly going to influence what's going to happen with the H3O plus. And what the slide simply says here is it says if we can preserve this ratio, then my pH is going to stay pretty much constant. If you have a big fluctuation in this ratio, then I got a big problem going on here. So with that said, in order to preserve that ratio, what we're going to look at is what is called the buffer capacity. And the buffer capacity is the amount of acid or base that can be neutralized by the buffer before we get this big swing in the actual pH. Well, one of the things that I know is that if I want to have a good buffer capacity, then what I really want is I want a lot of that weak acid, high concentration of it. And I also want a high concentration of its conjugate base as well. I want both of those, because if I keep the ratio really high, then once again, it prevents that fluctuation to actually take place. So we want high concentration. And once again, if I have a high concentration, then once again, that acid right here can really go in and attack any hydroxide out there. And then the same thing, if I have my conjugate base, it can go and attack any H3O plus out there. And if it does get used up a little bit, so be it. I got such a big concentration of the two that for all practical purposes, the ratio is still going to end up being the same. Will it change? Yes, it will. But it just won't be as dramatic. So in this class, we're always going to shoot for high concentrations of both the weak acid and also its conjugate base. To give you an example, what I've got right here is I've got the ratio, and we kind of talked about how the ratio would kind of influence things and how it's going to cause things to kind of fluctuate a little bit here. And what you'll notice is that this is going to be the actual setup where if we had 1 molar of each one of the weak acid, its conjugate base, it kind of looks at what would happen if we put in here an addition of a 0.01 molar H plus. So if I added H plus to this thing here, then I know who's going to go on the attack. It's going to be my base. It's going to be consumed a little bit. And that's why you'll notice that the base's concentration goes down a little bit, but the acid goes up a little bit. But because I'm starting off with fairly decent sized numbers here, they're going to notice that I'm going from a ratio of 1 to a ratio of 0.98. That's a 2% change with regards to the ratio. That's not that big. If I want it to be even smaller, let's choose a 10 molar and 10 molar. Let's choose 100 molar and 100 molar. And I can keep on making this percent go smaller and smaller and smaller with the degree of the change that's occurring between the ratio of the two. Right here, it simply says if I had something such as a low concentration of the two that I started off with. So instead of starting off with a 1 molar here and 1 molar here, say I started with 0.03 molars and 0.03 molars. If I add this still 0.01 molar to H plus, then once again, I know who's going to attack it. It's going to be the base. And as the base is being used up, I'm going to start producing some of that weak acid in this case. So you see, once again, the base is going down and the weak acid is going up. And if you look at it, it's still going down by the exact same degree. It went down by 1, this one went up, or down by 1. This one went up by 1. This one went up by 0.01. But because the numbers we started off with is such a big difference, then now you're talking about 50% difference that you're looking at here. So the moral of the story is, once again, we just want to make sure that we have a high concentration of both the weak acid and its conjugate base. Now, really quickly, we're going to talk about this thing known as the Henderson-Hasselbalch equation. Because when it comes to buffer problems, you get two choices. Choice number 1, right here. Run it right through the ice, write your Kas, substitute in for the Ks, figure out what the H3O plus is going to be, and then find what the pH is going to be. That's your choice. Don't have to do it though. Because one of the things that you're going to see for these buffer solutions is I just told you that we're always going to shoot for really high capacities. And because we're going to shoot for really high initial concentrations of the weak acid and its conjugate base, then something cool is going to kind of play out here. And the way I'm going to demonstrate this, so you kind of see what's going on here, I'm going to use a generic acid. I'm going to call it HX. This is my weak acid. And then I'm going to say plus H2O as a liquid, going in equilibrium in this case to produce H3O plus aqueous, plus I get my X minus aqueous. So just a generic sort of buffer solution. And once again, this is my conjugate base. Gotcha, conjugate base. So once again, this is a acidic buffer solution. I'll even write it up here, acidic buffer solution. All right, so let's just talk about what's going to happen here for these problems. What I would always start you off with in a buffer problem where I'm going to ask you to figure out what the pH is going to be, I'm going to give you the initial concentration of this acid here. So what I do right here, I'm going to say ice. Initial concentration. This concentration of the acid, HX, initial, is going to be very large because we want a high concentration. Over here in the ice process, this X minus initial is going to be also very large because we want a high concentration of both. When we start off, we want a really high buffer capacity here. So watch what's going to play out here. The change. Well, this is going to be 0 right here. So this, of course, is going to be minus X, this is going to be plus X, and this right here is going to be, I got to say initial. HX, initial. I'm messing this thing up. I'm not at the equilibrium yet. So once again, minus X and plus X here. Sorry about that. Now I'm going here and saying HX, initial. Once again, very large. Minus the X. Here I got plus X, then I got the concentration of X minus the conjugate base initial, once again, plus X. And this is very large. All right, watch what's going to happen here, because this is pretty cool. Because I'm starting off with very large concentrations of the weak acid and its conjugate base, what I know is always going to play out, and I know, watch carefully, that this test right here, Ka times 100, is going to always be less than the concentration of either the HX initial or the X minus initial. It's always going to pass, so it always passes the test. Always. which is going to be great for our buffer solutions. So the buffer solutions are going to pass it always, which means that we're always going to be able to do the following. And I'm going to show you how they got to the Henderson-Hasselbalch equation. We're always, for every single problem, we're going to be able to eliminate that minus x. Every single problem with buffer solution, we're going to be able to eliminate that plus x that sits right there. And what Henderson-Hasselbalch did, which you got to give him a little credit, but I don't know if you should be in every single chemistry textbook. He kind of noticed something that was going to be obvious. He simply said, okay, well, let me see something here. If I look at the actual Ka expression here, so I'm going to look at the Ka for this. I'm going to say, okay, Ka is going to be equal to products of reactants. Everybody raise their coefficients. No solids, no liquids, x minus over hx. All right, so watch what's going to happen. I'm going to change up expo markers. That one's kind of dying on me. Let's see if this one works a little bit better. Ah, that's perfect. What Henderson-Hasselbalch said, he's like, wait a second. All right, let me substitute in what I have right here into the expression. So I'm going to go in and say Ka is really just equal to, let's see, H3O plus concentration. When I substitute in, because once again, we said, hey, for the E part of the equilibrium, we got rid of the plus x that's sitting down here. So we just substituted in and said, hey, this is going to be x initial concentration divided by hx initial concentration here, because we got rid of the minus x sitting right here. And then what he did is he went one step further. He was like, okay, why don't I just solve this thing, since I'm gonna always get rid of the minus x and plus x, it's really just gonna be the initial concentrations, because they're so large that subtracting that little small x or adding a little small x is not gonna change those values. So he went in here and said, okay, well, let's do this. Let's solve this thing just directly for H3O plus, since the problem is always gonna ask me in this case, what is the pH of the solution? So he said, okay, H3O plus is gonna be equal to Ka, and I'm just solving this, so this is going to come over here, Hx initial divided by x minus initial. And therefore, for all the buffer problems, we can just throw in this case, our initial concentration of the weak acids, conjugate base, put the Ka right here, and we can always get the H3O plus concentration right here. But Henderson-Hasselbalch, it was like, wait a second. For all the problems that Mr. Harrelson asked, and also all the problems that College Board asked, they don't just ask for the H3O plus concentration, they ask for the pH. So he was like, wait, why don't I just do this? Why don't I just take the negative log of both sides here? And that's exactly what he did. He said, negative log, in this case of the H3O plus, is equal to the negative log, in this case of Ka, times the Hx initial divided by the x minus initial. And he said, hey, that's nothing more than pH. So pH is equal to, in this case, the negative log of the Ka times the Hx, all divided by the x minus. And once again, these are initial concentrations. But then he went one step further, because we couldn't stop right here and say, yeah, we'll just plug in this, it'll solve it. He was like, yeah, I'm going to do a little bit of things that I learned in my math class. I learned that technically I can do this. pH is equal to the negative log of Ka plus the negative log of Hx initial divided by the x minus initial. Got it. And then what he said, it's like, wait a second. pH is equal to the negative log of Ka, the pKa. Hey, I remember in math that if I have a negative here, and I want to make that into a positive and deal with logs, then I just flip these two things over, which means I can say plus the log of x minus initial divided by Hx. x initial. Hence, we now have what is called the Henderson Hasselbalch equation. Keep in mind, I will never ever ask you to derive this equation. This equation is on your equation sheet, so it's sitting there for you. And what you would notice is that if I wanted to figure out what the answer to this problem was, then I'm going to plug in, once again, the pK, and I'll plug in the initial concentrations into, and it's going to calculate what the pH is going to be in this case. Henderson Hasselbalch. Tomorrow, we're going to jump in and we're going to solve some buffer solutions using this equation. But all he did was just, once again, use the ice equation, recognizing that minus x and plus x are always going to be removed because we're dealing with these nice, large concentrations and we want a high buffer capacity, that this thing just kind of works out. It allows us to get to the actual pH. Now, tomorrow we talk about the homework assignment that you'll be working on over the weekend. I'm going to give you choices. I'm going to say you can use ice, because you could use ice to solve this problem. Or you can just dump it into Henderson Hasselbalch and let it just kick out what the answer is going to be in this case. All right. Now, one thing to point out. Since I am now done with this lecture, the only thing I'm going to ask for you to do is I'm going to ask you to verify that you've watched the video, and the way you're going to verify it. And once again, this is on the honor code, so you can't go off and tell your other friends like, hey, make sure you do this as well. You guys do this. Honor code, honor code, honor code. Remember, honor board, we're being honorable. You are going to simply email me your birthday. So literally, you don't have to say anything else. You can put it in the subject line if you want to. Just tell me your birthday. You don't have to tell me the year, because I know young ladies don't like to give away how old they are. So just your month and your date of your birthday. So month and day of your birthday. You'll email that to me in the subject line, and it'll verify that you watched the video, and that's it. We're done. There's no homework assignment for tonight. Only thing you have to do is just watch the video. Tomorrow we'll talk about the Henderson Hasselbalch equation really quickly, make sure everybody's okay with the buffer capacity, and then we're just moving on in this case. All right, this is where I'm going to stop. Thanks for watching the video.